Ever wondered why AI systems can sometimes be way too confident in their predictions? Imagine a self-driving car mistaking a stop sign for a yield sign, or a medical AI dismissing a rare disease because it's unusual. This is the crux of a critical problem in AI: how to make models aware of their own uncertainty. Today, we're diving into a groundbreaking approach called conflict-aware evidential deep learning, C-EDL, that's redefining how machines handle doubt. Deep learning models are powerful, but they're not perfect. When faced with data that's radically different from their training examples, like a snow-covered stop sign or a photo subtly altered by an attacker, they can make catastrophic errors. This is known as out-of-distribution, OOD data, and it's a huge risk in high-stakes fields like healthcare or autonomous systems. The challenge: teaching models to recognize when they're stepping outside their expertise. Enter Evidential Deep Learning, EDL, a technique that lets models quantify their confidence. Think of it as a student who says, "I think the answer is A, but I'm not 100% sure." EDL uses a mathematical tool called a Dirichlet distribution to model uncertainty in a single calculation. It's fast and efficient, but here's the catch: it's vulnerable to adversarial attacks. These are tiny, deliberate changes to input data that trick models into being overconfident. For example, altering a few pixels in an image can make a model see something that isn't there. So how do we fix this? That's where conflict-aware evidential deep learning, C-EDL, steps in. It's like giving the model a second opinion. Instead of relying on a single prediction, C-EDL generates multiple transformed versions of the same input. Think of it as viewing a photo from different angles or under varying lighting. Then it measures how much these predictions disagree. The more conflict, the more the model says, I'm not sure about this. Here's the magic. When C-EDL processes an input, it creates semantically meaningful variations, like rotating an image, adjusting brightness, or adding noise, while keeping the label the same. It then checks for contradictions in the model's predictions across these variations. If the model is confused, it increases its uncertainty estimate. This helps it detect OOD data or adversarial attacks without retraining. It's like having a GPS that's slightly less certain about your route, but way less likely to send you off a cliff. The results are impressive. In experiments, C-EDL reduced uncertainty coverage for OOD data by up to 55% and adversarial data by 90%, while maintaining high accuracy. For example, when tested on MNIST digits and fashion MNIST clothing, C-EDL kept OOD coverage under 2% across all metrics, while other methods struggled with leaks up to 4%. This means it's better at saying, "I don't know," when faced with something it hasn't seen before. But how does it work under the hood? The key lies in ablation studies, testing how small changes in the model's settings affect performance. Researchers found that tweaking parameters like transformation counts, how many variations the model checks, or penalty strengths, which control how aggressively it rejects uncertain cases, fine-tunes its balance between accuracy and security. For instance, more transformations reduce adversarial coverage but slow things down, a trade-off between speed and safety. Let's break it down with an example. Imagine training a model not just to classify images, but to question its own predictions. C-EDL does this by creating variations of input data that preserve the label but alter the appearance. If the model's answers clash across these variations, it knows something's off. This is especially effective against gradient-based attacks like L2PGD, where C-EDL, Meta, achieved 15.51% adversarial coverage, compared to over 50% for other methods. Even in non-gradient-based attacks, like salt and pepper noise, C-EDL hit near zero coverage at maximum perturbation strength. So why does this matter? In real-world AI applications, like self-driving cars or medical diagnostics, models need to be robust to unexpected inputs. C-EDL isn't just about accuracy, it's about safety. By teaching models to recognize their limits, we're building systems that are smarter, safer, and more trustworthy. Next time you see an AI making a decision, remember, it's not just about being right. It's also about knowing when to pause and question. Thanks for watching, stay curious, and we'll see you in the next video.